We will conclude our study of the introduction to functions by looking at inverse functions. And we begin with an example. The equation c equals 5/9 f minus 32 is used to convert the temperature from degree Fahrenheit into degrees Celsius. We will first solve for f, then convert the temperature 23 degrees centigrade into degree Fahrenheit, and plug this value back in to c of f and see what we get. So first, c equals 5/9 f minus 32. The first thing we should do is multiply by 9/5. And then we can add 32, and we find that f is going to be 32 plus 9/5 c. So this equation should give us a conversion from degrees centigrade into degrees Fahrenheit. So let's do it. So f of 23 is 32 plus 1/5 of 23. And if you do this out, you'll get approximately 73.4 degree Fahrenheit. So 23 degrees centigrade is about 73.4 degrees Fahrenheit. Well, now let's plug this into C. So C of 73.4 is 5/9 times 73.4 minus 32. And you'll find that this will give you approximately 23 degrees centigrade. Now this is interesting. Because you see that if we plug f of 23 into c, we got 23 back. So it seemed that c undid the f transformation. And that is the general idea of an inverse function. So consider a function from a domain D to a range R, where D and R are subsets of the real numbers, so R just contain real numbers. If x1 is in D, then by definition, there has to be a unique number y1 in R such that y1 is equal to f of x1. If instead we're given a number y2 in R, can we determine a unique corresponding x2 in D such that y2 is equal to f of x2? Now it is possible that there are two values in D that map to y2. It is also possible that y2 does not get mapped to at all. So in general, the answer to this question is no. However, if f is 1-to-1 and also onto, which means that every value in R has a corresponding value in D, then y2 is guaranteed to be mapped to by a unique value in D. That is, given a value y2 in R, it is possible to find a unique value x2 in D such that y2 is equal to f of x2. And we can only do this if only if f is both 1-to-1 and onto. So for any 1-to-1 and onto function, f from dr, a function g which has a domain R and a range D, is an inverse function of f if f of g of x is equal to x and g of f of x is equal to x for all x in D. We then write this, and this piece here, read f inverse of x. So this minus 1 is read as an inverse. So we have a function g of x is 1 over x minus 2, and we're asked whether that is an inverse of the function 1 over x plus 2. So to find out, let's first verify that f of g of x will give us x. Right, so this becomes f of 1 over x minus 2. So it's 1 over x minus 2 plus 2. Right, so minus 2 plus 2 is 0, so we have 1 over 1 minus x, which is just x. So that condition is satisfied. We now have to check if g of f of x gives us x. So this is g of 1 over x plus 2. So we get 1 over x plus 2 and then minus 2. I'm sorry. It's 1 over x plus 2 and then minus 2. So this gives, I'm going to rewrite that then. So it's 1 over x plus 2 minus 2. So we get x plus 2 minus 2, which is just x. So that condition is also satisfied. We can therefore say that g of x is an inverse of f, and write g of x equals f inverse of x. Well, now a natural question arises. Can a function have more than one inverse? So let's suppose that g and h are both inverse functions of f. So by definition, this would mean that f of g of x is equal to x, and f of h of x is equal to x for all x. Well, since x is equal to x, this would mean that f of g is equal to f of h. However, f is 1 to 1, since it has an inverse, which means that g is equal to h for all x. So g of x and h of x are equal. So this means that g and h were actually the same function all along. And so if f has an inverse function, then this inverse function is unique. So each function has its own unique inverse function, if it has one at all. We now use this fact to determine the inverse of a function. So find the inverse of the function 2 over x minus 3 plus 4. Now the first thing we should do is verify that this will even have an inverse. And we can do this by seeing if it's 1 to 1. Throughout this course, we're going to assume that every function we're working with will be defined in such a way that it is onto. So, suppose that f of x1 is equal to f of x2. And remember, when we studied one-to-one functions, what we have to do is show that x1 is equal to x2. So then this means that 2 over x1 minus 3 plus 4 has to equal 2 over x2 minus 3 plus 4. If we subtract 4 from both sides, we see that 2 over x1 minus 3 is equal to 2 over x2 minus 3. Dividing by 2, we find that 1 over x1 minus 3 has to equal 1 over x2 minus 3, which of course means that x1 minus 3 has to equal x2 minus 3, which of course means that x1 has to equal x2, and so therefore this function is 1-to-1. Now I'm now going to write the domain of f here. So what is the domain of this function? Well, it's everywhere where the denominator is not equal to 3. Or, I'm sorry, the denominator is not equal to 0, which is everywhere except where x is equal to 3. The range of this function, since this can never be 0, it'll be everything except for 0 plus 4. So negative infinity to 4. Right, now I no longer need any. So now to determine the inverse, suppose that y is equal to f of x. Then this of course means that y would be equal to 2 over x minus 3 plus 4. Now let's solve for x, right? Because we're trying to find this specific x value. So subtract 4, we have y minus 4 is equal to 2 over x minus 3. If we divide by 2, we get y minus 4 over 2 is 1 over x minus 3. Take the reciprocal of both sides. We have 2 over y minus 4 is equal to just x minus 3. And so 2 over y minus 4 plus 3 is equal to x. Now we can write f inverse of x, just switch the x and the y. So we have 2 over x minus 4 plus 3. So this is our inverse function. The domain of the inverse function is the range of the original function. So it'd be minus infinity to 4 unioned with 4 to infinity. The range of the inverse function is the domain of the original function. So you can see that in order to find the inverse of a given function, first just verify that it's 1-to-1. After that, set y is equal to f of x, solve for x, then switch the x and the y positions. Right, so what I did here mentally was I said that y is equal to 2 over x minus 4 plus 3. And then this is your inverse. So let's look at one more. Find the inverse of 2 plus the square root of x plus 4. So again, the first thing we want to do is show that it's 1-to-1. right? Because it's not 1 to 1, then it doesn't have an inverse. So this would mean that 2 plus the square root of x1 plus 4 is equal to 2 plus the square root of x2 plus 4. So this would mean that the square root of x1 plus 4 would have to equal the square root of x2 plus 4. Which means that x1 plus 4 has to equal x2 plus 4, which means that x1 is equal to x2, and so this is indeed 1 to 1. So the domain of the function, so remember you can't have a negative under the radical, but you can have 0, so it'd be negative 4 to infinity, and it's closed at negative 4. Now for the range, since this will always at least be 0, the range would be 2 to infinity. Again, I don't need any of this 1 to 1 stuff anymore. Right, so set y equal to f of x first. So that would mean that y is equal to 2 plus the square root of x plus 4. Subtracting 2, we get y minus 2 is equal to the square root of x plus 4. If we now square both sides, we get y minus 2 quantity squared is equal to x plus 4. And so the quantity of y minus 2 squared minus 4 is equal to x. And so the inverse would be the quantity of x minus 2 squared minus 4. Right? The domain is 2 to infinity, and the range is negative 4 to infinity. Again, because remember, the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. So that not only concludes our discussion of inverse functions, but it also concludes our study of introduction to functions. Starting in the next video, we will begin looking at and studying the several types of functions that you encounter.